Number system and encoding schemes. Mind map. Number systems and encoding schemes can be classified into different types, like types of number systems. Under that, we will get decimal number system, binary number system, octal number system, hexadecimal number system. Now, conversion between number system. Within this category, there are various subcategories: decimal to binary, decimal to octal, decimal to hexadecimal, binary to decimal, octal to decimal, hexadecimal to decimal. Encoding scheme: ASCII and Unicode. Types of number system. Number system is a method of representing numbers. Numbers can be classified into four major types: binary, octal, decimal, hexadecimal. Here are the details about these number systems. Binary number system, the base will be 2. The digits used are 0 and 1. Example is 101011. And we should write the base as a subscript. Octal number system. The base is 8. The digits used are 0, 1, 2, 3, 4, 5, 6, 7. So 0 to 7. Example 457. The base 8 should be written as a subscript. Decimal number system. The base is 10. So the digits used will be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So that means 0 to 9. Example says 398. Since the base is 10, so 10 should be written as a subscript. Hexadecimal number system. The base is 16. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. These are the digits used. So 0 to 9. And the rest 6 digits will be A, B, C, D, E and F. So this A represents 10, B represents 11, C represents 12, D represents 13, E represents 14, F represents 15. Example is AB37F. Since the base is 16, so that should be written as a subscript. Decimal number system. The number system which we use in our daily life is a decimal number system. In this, we make use of 10 unique digits: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 to form numbers. This number system based on 10 digits is also known as the base 10 number system. The digits in a number have a place value such as ones, tens, hundreds, and thousands. The place value is specified in powers of 10 in the decimal number system. So thus the numbers 189 and 2395 can also be expressed as 199 with base 10, that can be expressed as 1 into 10 to the power 2 plus 8 into 10 to the power 1 plus 9 into 10 to the power 0. 2395 of base 10 can be represented as 2 into 10 to the power 3 plus 3 into 10 to the power 2 plus 9 into 10 to the power 1 plus 5 into 10 to the power 0. Binary number system. In the binary number system, we make use of two digits 0 and 1 to form the numbers. This number system is also known as base 2 number system. The digits 0 and 1 are known as binary digits or bits. For example, the representation of a binary number would look like 1010 with the base of 2 that should be written as a subscript. Octal number system. Octal number system was devised for compact representation of binary systems. Octal number system uses 8 digits from 0 to 7. This number system is also known as base 8 number system. For example, the representation of an octal number would look like 175 with base 8. Hexadecimal number system. Hexadecimal numbers are also used for compact representation of binary numbers. It consists of 16 unique symbols, that is digits from 0 to 9 and letters from A to F. Here A is 10, B is 11, C is 12, D is 13, E is 14 and F is 15. This number system is also known as base 16 number system. For example, the representation of a hexadecimal number would look like A13 with base 16. Some areas where hexadecimal number system is used are to represent the address of a memory location, to define color codes used on web pages. For example, like color code for black, we will use the hexadecimal as 0000 and 00. That is in the form of decimal 0, 0 and 0. White can be represented in decimal as RGB value 255, 255 and 255. For that, hexadecimal representation will be FF, FF and FF. Red, the RGB value will be for in decimal 255, 0, 0 and in hexadecimal it should be represented as FF, FF and 00. Another usage of hexadecimal number system is to display system error messages. Conversion between number systems. Decimal number system is most commonly used in everyday life to measure physical quantities like height, weight, temperature, money, etc. Digital systems understand only binary numbers. Hexadecimal numbering system is often used by programmers to simplify the binary number system. Decimal to binary. This conversion uses repeated division method. In this method, the decimal number is repeatedly divided by 2 and the remainder is recorded. This process is continued till we reach a zero quotient. The result of the conversion is obtained by writing the remainders from the bottom to the top. The last number at the bottom is the most significant bit, that is the MSB. Example: convert 65 with base 10 to its equivalent in its binary number system. So first, 65 should be divided by 2. So the remainder will be 1, that is the LSB, and the quotient is 32. Again 32 should be divided by 2. Quotient we will get as 16 and the remainder as 0. Then again we should divide 16 by 2. The quotient we will get 8 and the remainder as 0. Again 8 should be divided by 2. We will get quotient as 4 and the remainder as 0. 4 divided by 2, we will get quotient as 2 and the remainder as 0. 2 again, if we divide by 2, we will get the quotient as 1 and the remainder as 0. Again, 1 should be divided by 2. Since 1 cannot be divided by 2, so the quotient will be 0 and the remainder will be 1. So this is the MSB. So now we will write the binary numbers from bottom to top, like from MSB to LSB. So the 65 with base 10 should be represented as 1 0 0 0 0 0 1 with base 2. Decimal to octal. This conversion also uses repeated division method. In this method, the decimal number is repeatedly divided by 8 and the remainder is recorded. This process is continued till we reach a zero quotient. The result of the conversion is obtained by writing the remainders from the bottom to the top. Example: convert 298 with base 10 to its equivalent in the octal number system. First, we will divide 298 with 8. We will get the quotient as 37 and the remainder as 2. Again, 37 should be divided by 8. We will get the quotient as 4 and the remainder as 5. Again, 4 should be divided by 8. Since 4 cannot be divided by 8, so quotient will be 0 and the remainder will be 4. So thus 298 with base 10 is equal to 452 in octal, that is 8 base. Decimal to hexadecimal. This conversion also uses repeated division method. In this method, the decimal number is repeatedly divided by 16 and the remainder is recorded. This process is continued till we reach a zero quotient. The result of the conversion is obtained by writing the remainders from the bottom to the top. Example: convert 537 with base 10 to its equivalent in the hexadecimal number system. Now 537 should be divided by 16. We will get the quotient as 33 and the remainder as 9. Again 33 should be divided by 16. We will get the quotient as 2 and remainder as 1. Again we should divide by 16. Since 2 cannot be divided by 16, so the quotient will be 0 and the remainder is 2. Thus 537 with base 10 is equal to 219 with base 16. Binary to decimal. Every bit in a binary number has a positional value associated with it. The positional value is in terms of increasing powers of 2, starting with the extreme right or the rightmost bit. The rightmost bit has a positional value of 2 to the power 0. The digits are multiplied with their positional values and the products are added to get the decimal number. Example 1. Convert 10011 with base 2 to its equivalent in the decimal number system. So we will write the positional value correspond to each binary number and then we will multiply it with the positional value and then we add up and we will get the answer. So thus 10011 with base 2 is equal to 90 with base 10. If you take a look, whenever the binary number is 1, we will just take the positional value of it. Whenever the binary number is 0, we need not to consider the positional value, as 0 multiplied by any number gives you always 0. Octal to decimal. The method to convert octal number to decimal number remains the same as to convert binary number to decimal number. However, in octal number system, the positional value is in terms of increasing powers of 8, starting with the extreme right or the rightmost digit. The rightmost digit has a positional value of 8 to the power 0. The digits are multiplied with their positional values and the products are added to get the decimal number. Example: convert 157 with base 8 to its equivalent in the decimal number. Now first we will write the octal number and the corresponding positional value of it. Then we will multiply the octal digit with their positional value and then add up. So we will get 111. So thus 157 with base 8 is equal to 111 with base 10. Hexadecimal to decimal. In hexadecimal number system, the positional value of the digits in terms of increasing powers of 16, starting with the extreme right or the rightmost digit. The rightmost digit has a positional value of 16 to the power 0. The digits are multiplied with their positional values and the products are added to get the decimal number. Example: convert A4C with base 16 to its equivalent in the decimal number system. First, we will write the hexadecimal number and we will write the corresponding positional value for each hexadecimal digit. Then we will multiply the hexadecimal digit with their corresponding positional value, and if we add up those values, we will get the equivalent decimal number. So thus A4C with base 16 is equal to 2636 with base 10. Now here we need to be very careful while multiplying. Like here A and C, these are letters. So first, before we multiply, we need to convert A and C value. As we know, A is equal to 10 and C is equal to 12. So first we convert those values to the digits or to the numbers, and then only we can multiply. Encoding scheme. We know that computer understands only binary language. That is the language of zeros and ones. Every character on the keyboard has a code associated with it. This code is called the ASCII code. Every time we press any key on the keyboard, the binary form of its ASCII code is sent to the computer. Just like ASCII, there are other standard encoding schemes where each letter, numeral, and symbol is encoded or assigned a unique code. ASCII. ASCII is one of the most common encoding standard. Every ASCII code makes use of 7 bits. It is possible to have 128 unique codes in the ASCII character set. ASCII code for some printable characters are given in the table below. Like space is represented as 32, @ is represented as 64. So in this way, small a is represented as 97 and capital A is represented as 65. So if we put the character A, then the binary equivalent of decimal value 65 is ASCII code, that is 1000001, that is in the binary form, is sent to the computer. Unicode. Unicode is an internationally recognized encoding standard that assigns a unique code to each letter, digit, or symbol used in any language of the world. ASCII represents only basic English characters, whereas Unicode supports characters from all languages around the world. Unicode is a superset of ASCII. The numeric codes 0 to 127 represent the same symbols in both ASCII and Unicode. This standard is supported by most of the software and allows data to be exchanged across different platforms, devices, and applications. Unicode can use 8 to 32 bits per character. Commonly used Unicode encodings are UTF-8, UTF-16, and UTF-32. So please subscribe to my channel for more videos. You will also get the PDF of this chapter or this topic in the description box. Thank you.